We've been spending some time building our understanding of multiple regression analysis, and now we're going to take a look at how this can be done using Python. We will use a data set that involves house prices, and if we take a look at the data, you can control-click to see the data set in a recognizable format. What we have are selling prices, assessed values. We also have the type of home, so this could be understood as a single family home or a condo perhaps. And we also have a time variable, which is the amount of time on the market. As we've been working on, we're going to try to predict the price of a home, the selling price of a home, based on the combination of these predictor variables. So we'll reference the concepts and also focus on the mechanics of how to do this with Python. The first step that you'll see in this corresponding notebook is the step to import the data. We've seen this a couple of times, but all we're doing here is modifying the URL, the web address, which points to actually a file in my Google Drive, and I've set it to share with anyone who has the link. We make some changes in order to turn it into a download URL, and then we make it so that we can use the read CSV from pandas. We can check to make sure that we've successfully imported the data to our notebook by checking the first 6 lines of the data set. We're going to take a look at some pre-processing steps. We always want to just take a look at the top of the data frame to see if it looks correct. Another method we can use is the keys method. This simply tells us the names of the variables in the data set. And that's going to be important, of course, when we need to fit models and things of that nature. We need to be able to refer to the variables correctly and make sure we notice when things are capitalized and so on. Some more pre-processing steps would involve taking a look at the shape of the data frame. This tells us what the dimensions are, how many rows and how many columns. So we have 30 rows of data, meaning we have 30 houses, and we have 4 columns. That tells us how many variables we're going to be studying. Another thing we might want to check is the data types. The data types should be integers or floats if we want to do some kind of numerical analysis, such as correlation analysis, if we want to build scatter plots, and if we want to fit a regression model. Most of the time we need to have integer or float variables. Okay, and those integer variables are zeros and ones, so even though they represent categories, we can treat them like numerical variables, and that's important for building the regression model in Python. I always like to show this step, even though most of our data sets don't have any missing values. It's so important to know if there are missing values. We don't get into the topic of dealing with missing data, but that in itself is a large topic that's worth spending some time on if you see yourself working with data a lot in the future. There are a lot of built-in methods for pandas that can help you replace missing values in sensible ways. After doing some pre-processing steps, a good thing to do is find a summary of all of the variables, and this gives us some common statistics such as the count, the mean, the standard deviation, and the 5-number summary. Notice that the 50th percentile is included. That's equivalent to the median of a data set. It's always a good idea to explore the data before fitting a model. And one of the reasons we look at correlations is to figure out if there are any variables, predictor variables, that are related to each other. Obviously, we care about whether the assessed value is related to the price, and it certainly appears to be related in this case because we have a correlation of 0.96, which tells us that the assessed value is closely related to the selling price. I'm not seeing any other high correlations. The time on the market doesn't seem to be closely related to the selling price because the correlation is 0.25. And the time also doesn't seem to be related to the assessed value either, which makes a lot of sense. So then we don't have to worry about predictor variables that are correlated with one another. If we did see high correlations between those predictor variables, we might consider leaving one of them out because we want to avoid inputting the same information into the model more than once. That can obscure the results of the statistical inference. So only put in information that's unique into the model. We've seen this before. This is another look at the correlation heat map, so we can see a visual of how those variables are related. And we want to pay attention to the key. The key shows us that the lighter values are associated with higher correlations. You can also take a look at a scatter plot matrix. The scatter plot matrix shows histograms and also scatter plots for the pairwise combinations of variables. It's helpful to see the histograms because then we can get a sense for how those variables are distributed. And one of the things we might be able to find out here is whether or not we should be transforming any of the variables like we did with the Gapminder data. Okay, final stage here is fitting the linear regression model. We did this with a bivariate relationship, but now we're going to do this with a multivariate relationship where we include multiple variables in the model. Okay. So you'll see once again, we're importing the necessary libraries. Something we may end up having to do is renaming the variables, and we can see that happening in lines 8 and 9. And the reason we do this is because we have to conform to the way we specify the model. So in line 13, I'm writing out the formula for the model. And I can't have spaces between the words for the names of the variables. So I've renamed them price and assessed so that I don't have spaces in those names because that can cause problems, unfortunately. So I do this and then I check and make sure that the data set looks okay. Okay, let's now look closely at this line 13. This is the important piece of the analysis. This is where we specify the model. We call it LM, short for linear model. Once again, we're using ordinary least squares, the common algorithm for finding the best approximation to the relationship. Optimizes a plane in 4-dimensional space in this case, I believe. So it's kind of hard to visualize, but it is an optimization problem, and there are multiple ways that can be accomplished. We'll use ordinary least squares. And we also want to specify the name of the data that we're using. And then we use the .fit method to fit the model to the data. The best way to look at the results is to use the .summary method. This gives us all of that information that tells us about the model, how well it performs, and what those coefficients are. After getting these results, we move to some interpretations, and those interpretations are included in these notes. I always take a look at the R-squared value. In multiple regression, we can look at the adjusted R-squared value that penalizes for the number of predictors. Statisticians are very conservative, so they avoid trying to exaggerate anything like predictive power or statistical significance. So we can go with the adjusted R-squared value, which tells us the percent of the pattern that's explained by this model. It seems like the model explains quite a bit of the pattern because, as we know, 100% would basically be the combination of variables explains everything about the model. In other words, knowing the predictor variables would help you perfectly predict values of the selling price. Of course, we have some unexplained variation because this number isn't 100%. We also care about the intercept and all of the coefficients and whether or not they are statistically significant. So as we saw in the last video, values close to 0 and specifically smaller than 0.05 suggest a statistically significant relationship between these individual variables and the response variable, which is the selling price. So I can see that the assessed value and the time are important, but the type doesn't seem to be statistically significant. So some statisticians might rerun the model with leaving that one out. We also can take a look at the F statistic, which is very large, and the associated p-value is very small, meaning that overall the model is meaningful. It is statistically significant. So some interpretations, remember that when we interpret the coefficients, we want to say that for each unit increase in the predictor variable, there's a corresponding blank change in the response variable. So we want to write that out in the context of the problem. So for the assessed value, we would say that for each increase of $1,000 in the assessed value, the model predicts an increase of $1,794 in the selling price. And notice I got that number from here. So this is the coefficient for assessed value. I changed it to thousands of dollars because I know that those are the units of this variable, and the price is also in terms of thousands of dollars. So just making it a little more intuitive. Let's take a look at another interpretation. For each additional day that a house is on the market, the model predicts an increase of 351 in the selling price. That's interesting to me because I thought it would be the other way around. In a lot of cases it is. For the type, when a home is a single family home, the model predicts an increase of $1,218 in the selling price. That is not statistically significant. And then finally, some additional interpretations. When all the variables are equal to 0, the model predicts a selling price of negative $128,287. This is the interpretation of the intercept, which is not meaningful, right? We're not going to have a house with a 0 assessed value, for example. And we talked about the R-squared value, and we talked about the value of the F statistic. So those are the key pieces to pull out of a multiple regression analysis. And that's a look at how to conduct a regression analysis with multiple variables using Python, specifically the Statsmodels library.